So hello, and welcome to the Booting with GRUB quick training from Linux Academy. What is GRUB? GRUB stands for the Grand Unified Bootloader, and it's a bootloader designed to boot multiple operating systems across a wide variety of hardware platforms and operating systems. Now, if you're not familiar with the term, bootloaders in general are very small pieces of executable code that provide just enough functionality to call another bootloader or to hand control of the CPU and the system to an operating system. Bootloaders let us make changes to the system environment prior to the OS being loaded. And one of the neat things about bootloaders is that they can be loaded on more than just disks. Bootloaders can be installed on partitions, loopback devices, anything that a PC might boot from. On the PC platform, which we're all pretty familiar, the initial system startup is started by something called the Basic Input-Output System, referred to as the BIOS for short. Historically speaking, PCs have relied on BIOS to supply information about storage device characteristics. That information, in turn, is usually passed to the bootloader, and from the bootloader to the operating system, or sometimes directly to the operating system. Now, BIOS was originally intended to work with a method of addressing known as CHS, which stands for Cylinder Head Sector. CHS has some really serious limitations. In its most modern form, without any translation or assistance, CHS can only address 504 megabytes. And because MBR and CHS are heavily tied together, very tightly coupled, CHS information is still passed from BIOS to the bootloader and sometimes to the operating system. But most operating systems ignore that information. Now, there is an alternative to BIOS that has been designed by Intel. This is called the Extensible Firmware Interface, or the Unified Extensible Firmware Interface. And its purpose as a whole is to replace BIOS as an interface and the limitations BIOS imposes. So in this quick start, I'm going to demonstrate the use of the following bootloaders. MBR, not directly, but we're going to see that MBR and GRUB, at least on computers that are booted from BIOS, are very closely related. When BIOS is involved, you can't get away from MBR, and that's just the nature of that hardware platform. We're going to look at legacy GRUB briefly, how to make configuration changes to it, because you do still sometimes encounter it in the wild. But legacy GRUB is deprecated, it's not being developed anymore, and so I'm not going to show how to install it. We're going to work extensively with GRUB 2, the follow-up to legacy GRUB. More specifically, we're going to look at some neat things like dual booting Linux alongside Windows, and doing some interesting troubleshooting for GRUB 2 in the GRUB CLI. Before we get started, we're going to take a quick look at some of the older technologies underpinning GRUB, specifically CHS and MBR, and that's to explain where the idiosyncrasies of bootloaders on the PC platform come from. So let's get started with that. Let's look at how we address block storage. Block storage refers to any system where an arbitrary number of bytes are bundled together in a single unit. USB devices, pen drives, floppy disks, old tape drives, CD-ROMs, and solid-state devices, as well as magnetic rotational devices like hard drives. These are all block storage devices. A lot of ways have been developed to address block storage, but the prevailing standard for hard drives, primarily rotational media, in the PC industry for a very long time was CHS. CHS doesn't just describe the amount of storage space available, it actually describes the characteristics of the storage device itself. And at the time, that was very useful. Ultimately, CHS was limited by its design. Backward compatibility was dauntingly difficult, and that means that each change to CHS deprecated or obviated, these words mean the same thing, a great deal of very expensive storage equipment and computer hardware. Keep in mind we're talking about computing in the 80s and 90s, when IBM was still making the PC, Microsoft was still releasing MS-DOS, and PCs were widely used and the majority of business computing hardware available. And so what does CHS actually stand for? When you look at a hard drive, if you were to take it apart, a magnetic rotational hard drive has a series of round platters that are spun on a spindle, which is basically a rod that goes through the center of these round platters. CHS stands for cylinder head sector, and that's how these platters were divided. Now, a cylinder and a track are sometimes mistaken for the same thing. That's not quite true. This diagram is an abstraction, and it's a simplification, but you can see here in yellow is highlighted what we would call a track. It's a discrete portion of the platter, and the various tracks resemble rings moving concentrically from the outside or the beginning of the platter to the inside. You'll notice that the platter is also divided by other lines that somewhat resemble a pizza, for lack of a better term. At the bottom, in the two arrows, the edges of one of those slices of pizza are highlighted. Now, the yellow track in between those two edges, that's a very crude abstraction or portrayal of what's called a sector. One thing I want to make clear right now is that the term boot block is synonymous with the term boot sector. They mean the same thing. The boot sector is a specific sector on the disk where system hardware may expect to find certain information, like the master boot record. We'll talk more about the master boot record shortly, but let's finish our discussion of So here we have our platters stacked on top of each other. There's a sector highlighted in yellow, and I've described to you what a track is. What a cylinder actually refers to is the vertical placement of sectors over one another on different platters. And the reason for this is that hard drive heads are not moved or were not moved independently of one another. So at any point in time when the hard drive heads were over a cylinder, each head was over the exact same area of its respective platter, so that you could take a laser beam, shoot it up through the stack of platters, and put a hole in the exact same spot in every platter. This is what's referred to by a cylinder. Now, the reason cylinders are so important, as we'll see here in a bit, is they are probably the biggest hindrance to CHS. Now, I understand that IBM designed CHS, and they were producing PCs that were reliant on BIOS. But why did they choose to build CHS or design it the way they did? I can't answer that question, but I can tell you that CHS was designed to meet the needs of IBM's BIOS, its basic input-output system. And that, in turn, was designed to meet the needs of the MS-DOS operating system. Because MS-DOS depended on BIOS, by proxy, MS-DOS depended on CHS. Now, with CHS and with BIOS, there are some interesting limitations. Computers that use BIOS expect to find boot code in the exact same location in RAM at every boot. Every single time you power that computer on, the CPU is expecting to find boot code at the exact same location in RAM. In a like fashion, BIOS expects to find the boot code in the exact same location on the hard drive or block device every single time it's powered on, and no matter what device is used. So if you swap hard drives out in a BIOS machine, even with new hard drive, BIOS expects to find the boot code at the exact same address. Now, the interesting thing here is that BIOS actually loads the boot code from the hard drive and puts it into RAM before the code is handed over to the CPU. Before the CPU even begins executing code, this is what BIOS does. For compatibility reasons, we find that BIOS systems still report CHS information to bootloaders and operating systems, but it's almost universally ignored. One of the things we have to be careful with certain CHS-dependent systems, especially older software, is to take care when we're accessing storage beyond 504 megabytes. Now, there were some methods designed to work around the CHS limitations. These were employed as translating layers to help operating systems negotiate CHS addressing, and one of the first was LBA, or logical block addressing, something that's still in use today. With LBA, each sector has its own unique address, and that address is unique across the entire storage device. Now, I'd be very surprised to find if the fourth track from the beginning of the disk actually starts at sector 200. Again, this is a very simple representation and an abstraction. But at the outside edge of the disk, where the first partition starts, sector 0 begins, and each sector is numbered sequentially all the way through to the end of the disk. With current implementations, LBA is capable of addressing about 128 petabytes of data. Now, there's something a lot like LBA called zone bit recording. And in zone bit recording, instead of sectors being numbered sequentially from the start of the disk to the end, sectors are numbered sequentially for every track on the disk. And it's just kind of a neat tidbit to know. Some devices allow for the thinning or the condensing of magnetic media on the platter so that each track has the same number of sectors. And some devices will allow the magnetic media to become much more or less dense so that performance increases or stays the same as you move across different areas of the platter. Now, solid-state devices are quite different from magnetic rotational media. Rotational media is an older technology, of course, and solid-state devices are much more closely related to the random access memory we have in our PCs. Despite this, they're still bound by the same limitations. If you have an SSD hard drive and you're using a BIOS-based computer, BIOS still expects to find the bootloader code in the same location, and all of the caveats apply in terms of CHS. Now, the translation to and from CHS is handled by the device because it doesn't actually have cylinders, although it does have sectors, but the same limitations do apply. So that wraps up our brief discussion about BIOS, master boot records, and cylinder head sector addressing. Not wonderfully exciting stuff, I know, but some of the critical functionality of GRUB surrounds these limitations and specifically provides workarounds. Operating systems like Linux or Unix, Solaris, VMS, or FreeBSD, these were not systems initially bound by the limitations of CHS or BIOS because they were designed on different hardware platforms. Now, as they were ported to the PC platform, suddenly they had to take these factors into play, and they had to deal with them just like every version of MS-DOS did, and just like every version of Windows has, clear up until Windows Server 2003, and clear up until Windows Vista. We're heavily dependent on BIOS, MBR, and CHS. Alright, so that's the end of this video. I will see you for the next. This is George Scott with Linux Academy.